726 feet of concrete stand between Lake Mead and the Colorado River basin below it. Inside that wall, there are hallways, not maintenance shafts, not narrow crawl spaces built for one engineer to squeeze through sideways. Actual corridors, tall enough to walk through two abreast, running for miles inside the body of Hoover Dam, looping through solid concrete like veins running through muscle. Somewhere down there, right now, water is trickling through a channel carved into the structure on purpose, and a gauge is quietly recording a pressure reading nobody outside will ever see. Most people assume a dam is exactly what it looks like from the outside. A solid plug of stone-hard concrete, poured once, left to sit there and absorb the weight of billions of gallons of water pressing against it forever. Solid all the way through, the way a boulder is solid. That's the intuitive answer. It feels obviously true. It's also wrong. If Hoover Dam had been built the way most people picture it, one continuous, uninterrupted pour of concrete from bedrock to crest, it would still be curing today. Not as a figure of speech, literally. Bureau of Reclamation Engineers calculated that a single monolithic pour of that scale would need roughly 125 years just to cool down to a stable temperature. Long before that clock ran out, the uneven cooling between the surface and the core would have torn the structure apart from the inside, cracking it before it ever held back a drop of the Colorado River. So the empty space isn't a design flaw, and it isn't a shortcut to save on materials. It's one of the only reasons the dam is still standing. By the end of this video, you'll understand why some of the most trusted, most permanent-looking structures on Earth are, on the inside, deliberately not solid, and why that hollow space might be the single smartest decision baked into the entire structure. The first explanation people reach for is weight. Less concrete means less material, and less material means a cheaper dam. That's true, as far as it goes. And it's not a stupid answer. Concrete is expensive to mix, expensive to pour, and expensive to move in the quantities a dam requires. Any structural engineer will tell you that shaving mass off a design saves money, sometimes a staggering amount of it. But weight isn't incidental to a dam like this. It's the entire operating principle. A gravity dam holds back a reservoir purely because its own mass is heavy enough to resist the water pushing against it. Carve out material in the wrong place, at the wrong depth, and you haven't built a cheaper dam. You've built a dam that tips forward under its own reservoir. The second explanation is access. Someone, eventually, has to get inside and check on things. So, of course, there are hallways. Sure, but access makes it sound almost incidental. A hallway bolted on afterward for convenience. The same way an office tower has service corridors tucked behind the drywall, invisible and unimportant to the building's actual function. That undersells what's really happening here by a wide margin. These corridors aren't an afterthought stapled onto the design. They're written into the dam's structural and thermal behavior from the very first line on the blueprint, poured in place before the surrounding concrete even finished curing around them. The third explanation, the one that sounds almost too simple to be the real answer, is drainage. Water gets into concrete eventually. Surely they just needed somewhere for it to go. This one lands closer to the truth than the other two, but it's still only a fragment of the picture. Drainage explains why a network of channels exists. It doesn't explain why that network had to be built into the dam before construction even finished. Why abandoning it for even a few years could put the entire structure at risk, or why the danger it protects against comes from a direction almost nobody thinks to worry about. Not the water pressing against the face of the dam, but the water working its way in from underneath. To get to the real answer, you have to stop picturing a dam as a wall and start picturing it as 3 or 4 separate engineering problems stacked on top of each other, all quietly solved by the same hollow space. Here's the first layer, and it starts with a question that sounds almost too simple. What actually kills concrete on a scale like this? Not water pressure, heat. When cement reacts with water, it doesn't just harden, it releases heat. The same chemical warmth you feel when you rub your hands together fast enough. In a thin sidewalk slab, that heat escapes into the open air within hours. No problem. In a mass measuring hundreds of feet thick in every direction, that heat has nowhere to go. The outer surface of the concrete cools quickly against the open air, while the core, insulated on every side by hundreds of feet of surrounding material, stays hot for months, sometimes years. That temperature gap between a cooling exterior and a still hot interior creates enormous internal stress. The same basic principle that shatters a drinking glass when you pour boiling water into it while the outside stays cold. Multiply that stress across a structure the size of a dam, holding back an entire reservoir, and the result isn't a hairline crack in a sidewalk. It's a structural failure waiting to happen in slow motion. Hoover Dam's engineers solved this with a technique that still sounds almost absurdly hands-on for a project this size. They didn't pour the dam as one continuous mass. They poured it in roughly 230 individual concrete columns, some of them 60 feet square, stacked one on top of the other in 5-foot layers called lifts. And before each layer set, they threaded steel pipe through the wet concrete. More than 580 miles of 1-inch pipe in total, enough to stretch from the construction site to well past Salt Lake City and back. River water, and later ice-cold water, pumped from an on-site refrigeration plant capable of producing 1,000 tons of ice a day, ran through those pipes to physically pull the heat out of the concrete from the inside, block by block, cooling in months what would have taken a century on its own. Once each column reached a stable temperature, engineers pumped grout into the pipes and sealed them permanently inside the concrete they had just helped save. They're still down there today, decades later, doing nothing at all. Silent proof of a problem that no longer exists, precisely because someone built a solution directly into the structure. But cooling pipes alone don't explain corridors wide enough to walk through decades later. For that, you need the second layer, and it starts with a claim that sounds almost backwards. The greatest long-term threat to a dam often isn't the water in front of it. It's the water underneath it. Water doesn't stop obediently at the dam's upstream face just because there's a wall in the way. It finds its way into the microscopic pores of the concrete and into the seams and fractures of the bedrock beneath the entire foundation, seeping downward and forward under enormous, relentless pressure day after day for as long as the reservoir exists. Given enough time and enough pressure, that seepage accumulates beneath the dam the way air gets trapped under a rug, pushing upward against the base of the structure from below. Engineers call this uplift, and it is exactly as dangerous as it sounds. A force trying to float the dam off its own foundation, working in a completely different direction from the force everyone assumes is the real danger, the water pushing horizontally, from the reservoir side. This is where the internal galleries earn their keep in a way no amount of raw concrete mass ever could. Drainage channels, bored downward from the lowest corridors deep in the structure, intercept that seepage before it can build into dangerous pressure, collecting the water and letting it drain away harmlessly, monitored the entire time by engineers walking those same corridors with nothing more sophisticated than simple measuring instruments, watching patiently, decade after decade, for any sudden change in flow that might signal a new crack, a failing seal, or a shifting seam somewhere in the foundation rock far below the visible surface. Take away that hollow network, and you don't just lose a convenience for maintenance crews. You lose the dam's only real defense against being lifted from beneath, silently, by the very reservoir it was built to hold. The third layer answers a question that follows naturally from the first two. How do you fix a problem you can't see, buried in bedrock, decades or even generations after the concrete has already set and cured? You go back through the tunnels you built the first time. At Hoover Dam, engineers spent 9 years, largely out of public view, drilling entirely new holes from the existing inspection galleries, deep into the surrounding bedrock to complete a supplemental grout curtain, essentially reinforcing the watertight seal beneath the dam from the inside out, without draining a single gallon from the reservoir and without touching the exposed public-facing surface at all. That kind of long-term, invisible repair is only possible because the corridors already existed, waiting, built into the design decades before anyone knew they'd be needed for this exact purpose. A truly solid dam has no such option available to it. Once a solid mass of concrete sets, its interior becomes permanently inaccessible except through demolition. A hollow dam stays alive, adjustable, correctable, for the entire length of its working life, which, for a structure like this, means the better part of a century. And counting. And then there's a fourth, quieter layer, easy to miss entirely, because it doesn't announce itself the way heat and uplift do. The corridors aren't just static tunnels sitting empty between inspections. They're instrumented, continuously, in ways that have only expanded as technology improved. Cables for seismic sensors that register the faintest tremor in the surrounding rock. Tubes feeding water pressure gauges. Wiring for temperature monitors that track the concrete's internal state in real time. All of it runs through the same galleries originally built for cooling and drainage. The hollow space inside the dam isn't only an escape valve for heat and water. It functions as the dam's nervous system, letting engineers a century after construction still listen to what's happening deep inside a structure they can no longer see through from the outside. The same way a doctor listens to a heartbeat through a stethoscope instead of cutting the patient open. Once you see it this way, you genuinely can't look at a dam the same way again. That smooth, silent concrete face isn't inert. It's a structure still being actively managed, decades or a century after the last truck of wet concrete rolled away, by people walking through corridors most visitors and most tourists never even know exist, checking drainage flow, checking pressure gauges, checking for the tiny early signs that, left unnoticed, precede catastrophic failure. This matters more than it might sound like it should. Because dam failures are not rare historical footnotes confined to old textbooks. They are catastrophic, often sudden, and almost always traceable to exactly the failure modes those hollow galleries exist to catch. Uplift pressure that built up unnoticed, seepage that went unmonitored for too long, a foundation crack that widened quietly for years before anyone was watching closely enough to catch it. The 1976 collapse of the Teton Dam in Idaho, an earthen structure rather than a concrete one, still stands as a stark reminder of what happens when internal seepage goes undetected until it's already too late. The dam failed within hours of the very first visible leak, killing 11 people and causing well over $1 billion in damage in a single afternoon. Concrete gravity dams are built differently, monitored differently, and designed with different failure modes in mind. But the underlying lesson translates directly. The danger a dam faces is rarely the water you can see pressing against its face. It's the water, the heat, and the pressure working quietly on the parts of the structure you can't see at all. So the next time you drive across a dam, or look down at one from a scenic overlook with a camera in hand, understand that the concrete beneath your feet is doing far more than simply blocking a river in place. It's actively managing forces trying to crack it from the inside and lift it from below, using a network of hollow space that engineers built in before the first drop of reservoir water ever touched the upstream face. Here's the detail that reframes everything you just learned. The corridors inside Hoover Dam are still there today, exactly as they were built, and the original cooling pipes are still embedded in the concrete walls, decades after they last carried a single drop of river water through them. Nobody ever came back to remove them once their job was finished. They were simply sealed permanently in place. Quiet scar tissue from a problem that was solved completely before the dam ever held back a single gallon of the Colorado River, and that hasn't needed solving again since. Every enormous concrete structure engineers have built since, later dams, eventually nuclear containment vessels. The deep foundations beneath the tallest buildings on Earth inherits lessons learned from those hollow corridors carved into a canyon wall almost a century ago. That raw mass alone never guarantees strength, and that the forces most likely to destroy a massive structure are usually the ones nobody can see from the outside. If, stories like this, the hidden systems, quietly, running underneath the world, you already thought you understood, are the kind of thing that keeps you curious long after the video ends. This is exactly what Discovery Loom exists for. Subscribe, and we'll keep pulling back the next curtain together.